Hello, Daniel and Blake. Let's take a look here at today's work, which is going to be 17.3, kind of a monumental occurrence. We are actually entering into the last section of the book. We may learn a few other things from earlier in the book before as we kind of wrap things up, but this is our last official section here, 17.3. And so we're going to look at our divergence theorem. I don't think today's will be too bad. There can be quite a bit of work on a couple of the problems, but I don't think the concept will be too bad. So let's take a look. So first, let's talk about what we're talking about when we talk about divergence. So if we have F being a vector field, F1, F2, F3, then we can say that the divergence of F is just what we call nabla dotted with F. And if you remember the nabla, that's simply ends up being, when we dot nabla with F, we get the derivative of the x term with respect to x, the derivative of the y term with respect to y, and the derivative of the z term with respect to z, all added together, is essentially what we get there. So it's like saying the vector of each term, and then we add it together. Or I should say the derivative of each term of the vector, then we add it together. So that's what we mean by divergence. So here comes our divergence theorem. So the theorem says, and this is our standard thing we're used to seeing, we've got a double integral, and this d sub w there, well, we're going to see that over some surface, if we want to think of it that way. And, or I should say w is actually a space, a three-dimensional space in essence. So if we take a look at doing the double integral over the derivative of this space, of the vector field F dotted with ds, then what we see is we can express that as a triple integral over the region W, remember that's a three-dimensional region there, of the divergence of F dv. So in the relationship here between W and derivative of W and S. This S is the surface. So if we go back and think about this, if you remember when we took the derivative of, say, for instance, the volume, we got the surface area. So going back, remember with circles, going way back to that whole idea of a circle, and if we had that situation where we have the volume of a sphere, I should say, was 4/3 pi r cubed. And then if we took the derivative of it, we got 4 pi r squared, which was actually the area there of, that was actually ends up being the surface area, is what we end up getting in that situation. So that's the same type of situation that we're looking at with regard to this situation here. So logically speaking, it kind of seems to make sense. Notice this is adding an extra integral, but instead of doing the vector field, we're doing the divergence of F. But notice the divergence of F is a type of calculation where we've essentially taken a derivative of this to add an extra integral in. The advantage to this is sometimes we can get an easy to evaluate triple integral here that's easier than doing this, particularly when we can get something here where this is just 1. If the divergence is 1, then we know that the triple integral over a region W dv is just the volume. And sometimes that volume is easy to calculate outright, and then we could find this integral fairly easily for something like that. So that gives you an idea the type of situation we're looking at. So let's take a look in example, or a couple examples. So number 4 just gives us a vector field and asks us to find divergence. This is very straightforward, but I thought I better do one just to make sure that you would see it done. So the divergence of F, taking the partial of the x component with respect to x, the derivative of the inside, x plus z is just 1, so we have 1 times, and the derivative of the sine is the cosine, and we keep it as x plus z. This is going to then be plus the derivative of 0 is 0, so it's plus 0. And then I'm going to go plus, and the derivative of this is going to be negative. So there's where my minus comes from. And the derivative of the inside here is x. So when I take the derivative with respect to z of this, so I get x, so I get a factor of x times, and then the derivative of e to something is just e to something. So I've got negative, and I end up with that extra x of a factor there. So I get xy e to the xz. Okay, that's divergence, pretty straightforward. Now let's look at the type of situation we're going to be looking at. So what we've got here on number 8, similar to what we did on the last section with the Stokes theorem, is we've got two different ways we can do this. We can directly evaluate this as a double integral here of f dotted with ds. We know how to do this. Or we can find the divergence and do it the triple integral way. And I picked one here that actually shows you where sometimes it is an advantage to do it the triple integral way. Seems a little counterintuitive that a triple would be easier, but in this case it will be. So we consider this shape here. What this is this produces a sphere of radius 2. And we have this given vector field here. So first let's go ahead and it says to confirm the divergence theorem, or actually I think the instructions say to verify it for the vector field in the region. So essentially what they want us to do is evaluate the integral using the vector field and evaluate the integral using the region and show that they're the same. So let's go ahead. So let's start in, we're going to first start with doing the vector field. So in order to do this, we have to parameterize our surface S. So our surface here is actually the exterior surface of the sphere. So we're going to parameterize that in terms of spherical coordinates. So we're going to use theta and phi. And so we're going to parameterize. We should be pretty familiar with what we're doing here. Parameterize that the following way. Then we have to get, I should say where, that's our, that gives us our entire sphere. Remember that our phi does not go 0 to pi over 2, because that would kind of like double count. Because if the theta is going around in a circle complete 2 pi, then the phi only has to go 180 degrees, and when you revolve it the full circle, you get the full circle there. So our phi just goes from 0 to pi. Now we need our normal vector. And this is one of those where you can go through and you can get the normal vector. You should be getting familiar with the idea that we take the partial with respect to theta, take the partial with respect to phi, get the cross product of the two, and we get our normal vector. But we also should be pretty familiar with what happens when we do this. Essentially what we get is we get the same thing as what we started with when we have a parameterizing a sphere like this, with an extra factor of sine of phi, and we get our, whatever our radius is here, we get it squared. So we end up with 4 instead of 2's here, and we end up with our cosine theta sine squared phi, so we're just getting that extra sine of phi in there. And so we see that extra sine of phi in all of those. So that's our normal. So now to go and do our, evaluate and do our integral, we need to take our vector field f, and we need to have it parameterized. We need to plug in our parameterization there. So our vector field f acting on our g function there. So we're putting in, this is our, notice our vector field was yxz, so this is y in parameterized form, this is x in parameterized form, and this is z. And then we need to go ahead and we need to actually do our double integral of the surface, which we have parameterized. So I'm using that 0 to 2 pi, 0 to pi. I've got my 8 here, because what I've done is I have to take the dot product of my normal and my f. So I've just done this dot product by looking at these and dot producting them as I go, and I notice that each one's going to have an 8. So I factored out the 8. And then I go along here and I see that I've got sine theta, cosine theta, sine cubed of phi, plus, and I see I've got a sine theta, cosine theta, sine cubed of phi, plus this cosine squared phi, sine phi, and that's d phi d theta. So at this point here, I could keep going. You can evaluate this and do all kinds of trig simplification and everything. But I kind of figured you didn't need to see me do that. You can go ahead and finish it off if you want to. But what you'll get 32 pi over 3. Fairly straightforward. So I actually started to do all that, and then I just realized it was a pretty big mess and it would have taken too long, so run out of paper. So there you go. All right, now let's do it the other way. Remember, the other way, what we have to do is we have to find the divergence of our vector field. Well, the divergence of our vector field is pretty straightforward. Remember, it's y, x, z. So first I take the derivative of the x component, which is y with respect to x. That's 0. The derivative of the y component with respect to y, that's the derivative of x with respect to y, that's 0. And then the derivative of the z component, which is z with respect to z, that's 1. So our divergence is 1. So that means that using 1 here, we know that we've got the triple integral over our region W, 1 dv. But this formula here, we know when we take a triple integral over a given region with 1 dv, that's just a formula for the volume of that region. So that's just equal to the volume of that sphere, and I know how to find the volume of a sphere. It's 4/3 pi r cubed, and my radius here is 2, so I get 32 pi over 3. And so I have verified that I get the same result. And you can see in this case how much easier it is to use the divergence theorem than it would be to do this, because this here took quite a bit of work, and I didn't even do all the work. Okay, I kind of got to here and said, yeah, if I keep going, I'll get to this. Here, that's all the work that was required, and I did all the work. So you can see how much of an advantage it is at times to use a divergence theorem. Okay, so we're going to do 17.3, 1 through 9 odd. 1 and 3 should be very easy. They're finding divergence. 5, 7, and 9, they'll make you work a little bit more on those. But I think that they shouldn't be too bad on those. So let's go ahead and have you guys start those. And I should have your test graded today and be posting those. I've got the answer key made up, and I've looked a little bit at them, but I haven't just been able to finish it. But I will finish it off and get it back to you. Okay, with that, hope things are going well, and we will have a Zoom session tomorrow if you have questions.